But we could not really proceed further for quite some while because of crystal polymorphism. The crystals varied by as much as 10 angstroms along one unit cell direction, making it virtually impossible to proceed to high resolution. That difficulty was overcome some years later by Patrick Cromer and Dave Bushnell, who happened on a way of shrinking the crystals by as much as 20 angstroms along that one unit cell direction, and now the crystals were uniform from one to the next, isomorphous. And we could employ the commonly used method of multiple isomorphous replacement with heavy atom derivatives. We encountered the final difficulty that none of the 50 or so compounds commonly used for that purpose proved applicable to the polymerase problem, and some further time elapsed before we finally discovered some non-standard compounds, an iridium compound and also a rhenium compound that were suitable for our purpose. All of this took a long time, more than 10 years from the discovery of lateral fusion to the formation of two-dimensional protein crystals, almost another 10 years, to RNA polymerase II crystals and 3D crystals derived from the 2D crystals. And then another 10 years, 10,000 liters of yeast, and a graduate student went into the final solution of the problem. You see here Dave Bushnell lowering Ken Westover into the 200-liter fermenter that we used over the years to produce all the yeast for the work. Ken was able to repair a valve at the bottom that needs attention from time to time. Ken is not only a fine young scientist, but also a gymnast, and slender and fit enough to perform this necessary task. Ken was an MD PhD student. He completed the PhD part of his work and has gone on to the clinics, and I don't know if we'll ever find another student of his caliber. So the structure that we solved was, as I have mentioned, of a 10 subunit molecule, more than 3,500 amino acids, more than 28,000 non-hydrogen atoms, initially to a resolution of 2.8 angstroms, and most recently 2.3 angstroms resolution. Now, this slide shows you the structure in the form of a ribbon diagram with different colors for the 10 different subunits, and I call your attention to the one here in purple. This is the 5th largest subunit. It is, so to speak, a typical 25,000 Dalton protein, which gives you a sense of scale of the enormous structure. Now, I'll also take advantage of this slide to introduce 4 views of the structure that I will then show throughout all the rest of the lecture. Now, the first is a view that you see here we refer to